Welcome to Module 10. This is Inferences for Population Standard Deviations. Our objectives for this module will be to explain the role of variation in statistical analysis and why standard deviation is important when we're evaluating data quality. We're going to conduct and interpret hypothesis tests for a single population standard deviation, as well as the confidence interval procedure that goes with that. And then we're going to compare the variability of two populations using statistical methods for two population standard deviations. And we'll also look at the confidence interval procedure for that as well. Let's again consider the standard deviation. The standard deviation is a measure of variation or spread of our data set. And so for a variable x, the standard deviation of all possible observations for an entire population is called our population standard deviation. And it's always going to be denoted with the symbol sigma as shown here. And sometimes you'll see it as sigma and then there'll be like a subscript of an X or a different letter. But when there's no confusion about what we're doing, we'll just simply put the sigma. So suppose that you want to get some information about a population standard deviation. Now, if your population is really small, you can actually just take a census and then you can compute your standard deviation from that population data. But we've talked about this before, and we know that most of the time that's just not feasible for us because populations tend to be quite large. And so instead, we use inferential methods to get the required information that we need about the standard deviation. One of the most universally difficult thing about statistics is understanding when to use which type of test, depending on the information you have. So when would we use the population standard deviation? I have a little summary of a few things that you would look for. So the true population variability is already known. It might come from a large historical data set or some validated measurement systems. And you're testing a population mean. But more importantly, I wanted to give you guys some examples of where you might actually see this type of statistical analysis in your field of study. So one example is in pharmaceutical manufacturing. So pharmaceutical companies will produce tablets, for example, and they have different milligrams to them. And so, for example, you could have a company that produces 500 milligram tablets of some sort of medication. And you'd have years of production data. And so from that information, you can get a population standard deviation of how much that tablet actually weighs. And so researchers can use this information to test a new machine calibration, for example. Another thing that you guys might come across in your day to day is something like a blood analyzer machine at a hospital. So hospital lab machines can measure things like your blood sodium concentration, and through calibration testing, the machine's measurement variability or its standard deviation can be really well known. And so researchers might look at it to see if the machine itself is producing biased results, for example. Because the measurement variability is already established, you can use the inferential statistics to get some averages that might differ from an expected value. This is true for blood pressure monitoring as well, and you might see this in quality control in medical devices. So manufacturers produce insulin pumps, for example, and they need to deliver really precise doses. And you can get long-term production data and establish standard deviations for things like insulin pumps. Because the population variability is known from historical data, then you can use that to make some decisions and get some information that you need. So now let's talk about how to perform hypothesis tests and construct confidence intervals for standard deviation of a normally distributed variable. Now, such inferences are based on a distribution called the chi-squared distribution, and it is pronounced chi, and I have so many people who call it chai or chi. I will make fun of you. So it is a chi distribution, and it's based on a Greek letter, and it's got this kind of lowercase fancy looking x. And so you can use that in the symbols tab, but often you can just do an actual X and no one's going to ding you on marks or anything for that. So the chi-square distribution, a variable has this distribution if its distribution is the shape of a special type of right skewed curve. So if you look at this figure here, you can see that all of these guys have tails that are pointing to the right, and that means that they are right skewed. So there are infinitely many chi-square distributions, just like with the other distributions we looked at, and we identified the chi-square distribution and its curve based on the number of degrees of freedom, and we did this for the t distribution. So in this figure, it's showing three different chi-square curves, and it's illustrating some of the basic properties about the chi-square curve that we'll talk about. But just note that as your DF goes up, so you can see the orange one here, it's a DF of 19, it's starting to look more and more like a normal distribution the larger your sample size. I was listening back to make sure that everything sounded okay in the video, and you guys can tell I have a cold. I was trying to hide it. I am sorry. I'm kind of sniffly, so please excuse my disgusting noise sounds, and hopefully I'll get over this cold quickly. So the basic properties of the chi-square curve, and this is very similar to what we've looked at with our other types of distributions. So property one is that the total area under the chi-square curve equals 1. A chi-square curve starts at 0 on the horizontal axis, and it extends indefinitely to the right, approaching but never touching the horizontal axis as it does so, and this is an asymptote. A chi-square curve is right skewed, and as the number of degrees of freedom become larger, chi-square curves look increasingly like our normal curve. Okay, so let's get into looking at the chi-square table, because this is similar to the t-table, and we're going to have to use this chi-square table to do some of our calculations. So if you grab out your formula card and your tables, you will find the chi-square table, and you'll see the chi-square symbol at the top of it. So in this example here, it's saying for a chi-square curve with 12 degrees of freedom, find chi-square of 0.025. That is, find the chi-square having an area of 0.025 to its right as shown in the figure below. So make sure that you grab out your table and try to follow along with me. So when you're looking at this table, you're going to have a column and they're going to be your degrees of freedom. And then along the top, you're going to have the chi-square values with the significance levels with it across the top. So what you can do here is you will look for 12 degrees of freedom. So go down your DF line, go to your 12 degrees of freedom, and we're looking for a chi-square of 0.025, and you just match that up with the row along the top that has chi-square 0.025, and what you'll end up with is 23.337. So one thing you'll notice about the chi-square table is that the values are actually quite large on it compared to what you guys are used to doing. Okay, this example here is a little bit different. It's asking us to find the chi-square value having a specified area to its left. And so in this one, it's a 0.05 to its left. And because of the properties of the chi-square, we would take 1 minus 0.05, and we would end up with 0.95. But if you look at your chi-square table and you look across the top, you'll see that there is no chi-square for 0.95. And that's because I've given you an incomplete table. So if I'm ever going to get you to look up something for the left-hand side, I'm also going to give you a table with more numbers on it. But one thing that you can do is use this really interesting approximation called the complement. So what happens here is that for a chi-square that has a DF, and in this case it is a DF of 7, which is really small, and we want to find the chi-square that is the right tail critical value for alpha, then the left tail critical value for the probability alpha is not directly in the table, but you could approximate it by taking 2 and multiplying it by your DF, and so in this case it would be 7, so 2 times 7, minus the right-tailed chi-square. And in this case, that right-tailed chi-square is like 14.067. Okay, so if you looked at 7 and you went to the chi-square of 0.05, you're going to get 14.067. So we could use the complement by taking 2 times 7 minus the 14.06, and then we would get an approximation. Now, if you actually go through with that calculation, you'll find that that number is negative, and we can't have that. That's not a number that we can use. So what we're going to do for this one is I'm only going to give you the upper tail table, and so I don't expect you to calculate the exact left tail values for a really small DF. I will give you the right tail column, and I will only ask the upper tailed test, or I'll give you a new table to do that. In this example, we want to find our chi-square value for a specified area. So for a chi-square curve with a DF of 20, determine the two chi-square values that divide the area under the curve into a middle 0.95 area. And remember, this all equals 1. So both of those sides together should equal 5, so that 0.95 plus 5 is equal to 1. So first, what you want to do is you want to find the chi-square value on the right. And you can see that in the figure that I've shown here. I'll just get my little highlighter out here. And so you could see that in here. So we're going to shade the area on the right in 0.025, right? This just helps us to keep things on track. Now, from our table, we can go to our DF of 20 and our chi-square of 0.025, and we will find the number 34.170. But next, we want to find the chi-square value on the left. And because the area to the left of the chi-square value is also 0.025, the area to its right is 1 minus 0.025, and so of course we'll get 0.975. Then you could use a more complete table, and you would be able to go for a DF of 0.975, and you would come up with the value 9.591. And don't forget, you could also use the approximation where you can take 2 multiplied by the DF and then subtracting the number that you got for the other side. This leads us to key fact 11.2, the sampling distribution of the sample standard deviation. Suppose that a variable of a population is normally distributed with a standard deviation, sigma, then for samples of size n, the variable chi-square is equal to n minus 1 divided by sigma squared multiplied by S2, and this has a chi-square distribution with n minus 1 degrees of freedom. With our key fact in mind, let's look at an example. According to the key fact, for samples of size 10, the variable is equal to the equation that we have on the slide here, and this is the equation that we showed last time. And it has a chi-square distribution of 9 degrees of freedom, because remember, it's n minus 1. Now, we could use a simulation to show that this fact is quite plausible. So what's shown down here is that there was a simulation of 1,000 samples of 10 capsule weights for a certain medical drug called Xenical, and this is actually like a weight loss drug. Anyways, so there were 1,000 samples of 10 observations, each of a normally distributed variable that had a mean of 120 and a standard deviation of 2. So then for each of those 1,000 samples, we can determine the sample standard deviation, or S, and then get a value of the variable to display. And what we have is an output here of the histogram of those 1,000 values. And what that's showing is that the chi-square is shaped with that kind of special sort of right skew to it. And over top, we've superimposed the chi-square with the df of 9. And so this is just to show you that the sampling distribution of the sample standard deviation is in fact true, so that we can now go forward with our inferences. Okay, we're going to look at the hypothesis test for the population standard deviation. And I just want to take a step back for a second. First of all, I will post the greater chi-square table for you guys to use. And also, I know that a lot of this stuff that we're talking about today is a little bit out of reach. It's new and it's a little bit weird. And so some of the things I'm showing you, it's more for like the theoretical background. And don't worry, I'll be very clear about what you actually will have to know how to calculate. So anyways, let's talk about the hypothesis test for the population standard deviation. So we already know our key fact, and it leads to the formula that I'm showing here on the page. And this will lead us to our one standard deviation chi-square test. And we'll go through the procedure for it. But I did want to mention that a couple things. First of all, we're going to use more so going forward, we're going to use the critical value approach when we're using tables, because calculating or just because we don't actually calculate the p-value, we're always estimating it from the tables. And as we're moving forward with these different tables, it becomes really awkward and tedious. And so for p-values, we're probably just going to be using more statistical software to calculate them, or I'll give you a p-value so that you could use that to assess other things. Otherwise, you're going to have to use the critical value approach. Another thing that's a little bit different here is that unlike our z-tests or t-tests for one or two population means, the one standard deviation test is not robust to violations of that normality assumption. So it's really very bad for that. So you always have to make sure that you're checking for that normal population. And of course, if it does not meet your normality requirements, then we would advise that you move on. I left you hanging on the last slide, so we would advise that you move on to a non-parametric test. Okay, so here's the procedure for the one standard deviation chi-square test, and the purpose is to perform a hypothesis test for a population standard deviation sigma. Our assumptions are that it's a simple random sample and that it has a normal population, and remember, it is not robust to a violation of this. The null hypothesis here is going to be that your standard deviation is equal to your secondary standard deviation. And then we have our alternatives where it can be two-tailed, left-tailed, or right-tailed. We'll decide on our significance level alpha, and then we compute the value of the test statistic using this formula here. And the same as it was before, there are the two approaches that we can take to make a decision. Now, the first one is the critical value approach located here, and everything is pretty much the same. And then we also have the p-value approach. Now, remember, we're going to start using the p-value or obtaining our p-value with technology, with calculators, or I'll just give you a p-value so that you can use that to make some decisions. And then finally, don't forget to interpret the results of your hypothesis test. Quite a few of you guys are forgetting to do that, and you're losing some really easy marks. Okay, let's walk through a hypothesis test. So a sample of 10 Xenical capsules have weights in milligrams, and it's shown in this table here. At the 5% significance level, do the data provide sufficient evidence to conclude that the standard deviation of the weights of all Xenical capsules is less than 2.0 milligrams? Okay, so first things first, we've got this table of information. Now, remember, when you have a table of information like this, you could do a whole lot of stuff with it. You can calculate a standard deviation, you can calculate a mean. And if you're given a table of data, chances are you have to do that thing. I'm really surprised the number of you guys that do not know how to calculate the standard deviation properly. You use the wrong formula most of the time. You need to be using this formula here, but it would have a square root over it. This here is the computational formula. If you're using the theoretical critical formula, you're adding steps and decreasing your precision. So make sure on your formula card, you're checking to see which formulas you're using. Now, if we took this data and we put it on a QQ plot and we look for normality, this one's pretty normal. It's got a little bit of a curve here, but the sample size is quite small. So we're just going to go ahead with this one and say, yeah, it's pretty normal. Now, don't forget that you could also run a Shapiro-Wilk in this situation as well. All right, so our null hypothesis in this one is that there's the standard deviation is equal to 2.0 milligrams, so there's too much weight variation for each of those capsules. And then we've got our alternative hypothesis, and keep in mind that this is left-tailed, right? So it's saying that the standard deviation is actually going to be less than 2.0, and there wouldn't be not too much weight variation then. The test is going to be performed at the 5% level of significance, or your alpha is equal to 0.05. So we are wanting to calculate our chi-square, but if you look at the information down here, we don't have everything we need. What we're missing here is this s squared, or our standard deviation calculation. So go back and make sure that you know how to calculate this, because a lot of you guys are getting this part wrong. So it is the sum of x squared minus the sum of x squared on the outside divided by n over n minus 1. So what you're doing here is you're going to take all of these values here and you're going to sum them together. That number is going to go in right here and they'll square it on the outside. Then you'll take all of these numbers and you will square every single one of those numbers. You will sum them together and that number goes right here. And the rest of it is pretty easy. And you end up with 1.113. Now, we can now use our chi-square equation because we know n is equal to 10 and we've got a standard deviation of 2.0 and we've just calculated this s. We could just put all of this information now into this formula. So it ends up being 10 minus 1 over 2.0 squared times 1.113. And the test statistic that we calculated is 2.504. And now we need to make some decisions. So on the left-hand side of the page, I have the critical value approach. And so for this one here, we have an alpha of 0.05, but we also have a DF of 10 minus 1 or 9. So you could determine the critical value here by taking your 1 minus alpha, and you will end up with 0.95. And I'm just going to tell you that this number here will end up being 3.325. And again, you could use your broader table off of Blackboard to calculate that critical value. Now you're just going to compare this number here to your critical value here and then state if it falls within the rejection region or not within the rejection region. The same with the p-value approach, just knowing that this p-value here is going to be calculated from technology. You couldn't have gotten this anywhere else at this point. And so we'll look at the p-value here of 0.01, and we specified our significance level at 0.05. So to interpret this, for both the critical value approach and the p-value approach at the 5% significance level, the data provides sufficient evidence to conclude that the standard deviations of the weights of all the Xenical capsules is less than 2.0 milligrams. So the test results here, we're showing that we are rejecting our null hypothesis. We could also get a confidence interval procedure for a population standard deviation, and we do call this the one standard deviation interval procedure, and I'm going to go through the steps with you. Like the one standard deviation hypothesis test, this procedure is not robust to the violations of the normality assumption. Here's the procedure for the one standard deviation chi-square interval procedure. The purpose is to find a confidence interval for a population standard deviations. Our assumptions is that it's a simple random sample and that we have a normal population. And for our step 1, we have a confidence level of 1 minus alpha and a DF of n minus 1. To calculate the actual confidence interval, it's going to be from this to this here. Okay, so we'll go through an example of it. The thing that changes here is the denominator. So we've got our chi-square alpha divided by 2, and then we've got our chi-square 1 minus alpha divided by 2, and that will give you those bookends of your lower and upper limits. And we're going to continue with our zedical capsules example. Use the sample data to determine a 90% confidence interval for the standard deviation of the weights of all zedical capsules. Okay, so for our step 1, we need to find a confidence level of 1 minus alpha, and then we use our table to find the chi-square 1 minus alpha divided by 2, and then our chi-square alpha divided by 2 with a df of n minus 1. So for a 90% confidence interval, the confidence level is 0.90, which is equal to 1 minus 0.10. And so our alpha is 0.10. For an n equaling 10, we have a df of 9. All right, so these two sections here are the ones that you're going to have to use your table for. We can start down here because you probably have the table in front of you, and if you take 0.10 and you divide that by 2, then of course you're going to get 0.05. So we also know that we have a df of 9. So look on your table for 9 and then go across and look for your 0.05, and you're going to get 16.919. And it's the same thing for this one up here, but you're going to have to use the broader table to get to it. Okay, so once you have these two numbers, then you pop them into your equation here. All the rest of this stuff you already have, and so then you'll get your lower and your upper bookend for this, and the answer is 0.77 to 1.75, or 4, sorry. So we could be 90% confident that the standard deviation of the weights of all the zedical capsules is somewhere between 0.77 milligrams and 1.74 milligrams. Okay, guys, I really encourage you to go back through that chi-square stuff and make sure you know how to calculate it as well. It's really easy to listen to somebody talk about it when all of the answers are there for you, but you have to be able to do it on your own as well. And you guys have been really good for that so far. All right, so now we're going to talk about inferences for two population standard deviations when we use two independent samples. So more precisely, we're examining inferences to compare the standard deviation of one variable of two different populations. And this is based on something that we call the F distribution. So this is a whole new table. All right, I'll introduce the F distribution to you. A variable is said to have an F distribution if its distribution has the shape of a special type of right skewed curve, and we call this our F curve. Now, there are infinitely many F distributions, just like with our other ones, and we base it on the number of degrees of freedom, just like we did for the T distribution and the chi-square distribution. What's different though about the F distribution is that there are two numbers of degrees of freedom instead of just one. And so in this picture here, you can see each df, it's df equals 9 and 50, and df equals 10 and 2. And so you're always going to have 2 degrees of freedom. Now, the first number of degrees of freedom for your F curve is from the numerator, and the second degrees of freedom is from the denominator. And we'll talk about that more as we go. We've talked about degrees of freedom in the past, but I don't think we've ever really thoroughly defined it. So I want to take the opportunity to do that now. Now, the degrees of freedom, or your DF, this is the number of values in a calculation that are free to vary after certain information is already known or fixed. So a really helpful way of thinking about this is to think about your degrees of freedom like currency you spend to run a statistical test. When you run a test, you need information. Each piece of information is like 1 unit of current currency you can spend. So you can think of it like $1. The degrees of freedom is the amount of statistical currency you have available to use. And so again, down here, I'm just showing that for the F distribution, you're always going to have two. You're going to have a degrees of freedom for your numerator, which is always shown first, and then you're going to have a degrees of freedom for your denominator. So I'm going to give you guys a kind of a simplistic example that I hope will help with understanding this. Suppose you have 5 data points. Now, at first, it looks like you have 5 pieces of information, like $5. But if you calculate the sample mean, you've already used some of the information because the data now has to satisfy that mean. So once the mean is fixed, there's one value that you've spent that's no longer free to vary. So now you only have 4 independent pieces of information left. Your degrees of freedom is 4. Why does this matter? It matters because statistical tests like your t-test, your chi-square test, and anything that's using the F distribution require degrees of freedom to determine which probability distribution to use, how wide the tails of your distribution are, and how much uncertainty might exist in your estimate. So a really simple way to think of it is the degrees of freedom are the amount of independent information you can spend to estimate variability or run a statistical test. Let's talk about the basic properties of our F curve, and this is going to be almost annoyingly familiar to you. The total area under an F curve equals 1. An F curve starts at 0 on the horizontal axis and extends indefinitely to the right, approaching but never touching the horizontal axis as it does so, and that's called an asymptote. And an F curve is right skewed. Okay, make sure that you grab out your table, your F table from your statistical package formula card tables that you were given, and grab that out so that you can follow along with me on this one. So what we've got here is an example where we want to find an F curve with a DF of 4 and 12. Find 0.05. So that they want us to find the F value having an area of 0.05 to its right. So if you grab out your table first, what you're going to see is that we've got F values, and they are corresponding with alpha values. And this will be the first column that you see. It says DFD, and that stands for the DF of the denominator. And then you've got an alpha value. And then along the row at the top, it says DFN, and that indicates the degrees of freedom that you would have in your numerator. And if you don't remember which one is which, just go back a slide and I've got it listed out. So to get the F value that we need for this, in this case it's alpha 0.05, the numerator here is 4, and the degrees of freedom for the denominator is 12. And of course, we have alpha. So we first go down the DFD column to 12. Next, concentrate on the row for alpha labeled 0.05. Then go across the row to the column that is labeled 4. And if you do all of that, what you will end up getting is 3.26. And so that will be the answer that we have here. So make sure you try this with your table. So what you're going to find is that with many of the different statistics that we do that involve that F distribution, we also need to determine F values having areas that might be 0.005 or 0.01 or 0.025 to the left. So these values aren't directly available from the table, but you can get them indirectly from the table by using this key fact. Key fact 11.4, reciprocal property of F curves. For an F curve with a DF, and it will just be value 1 and value 2, the F value having area alpha to its left equals the reciprocal of the F value having area alpha to its right for a F curve with a DF having the values of 2 and 1. So let's do an example of that. In this example, it's saying to us for an F curve with a DF, which is 60, and then 8, so our numerator, then the denominator, find the F value having area 0.05 to its left. And so we can apply our key fact that we had on the reciprocal property of F curves. So the required F value is the reciprocal of the F value having area 0.05 to its right for an F curve with a DF of 8 and 60. So if you look at your table, what we've got is the latter F value equals 2.10. And so consequently, the required F value is 1 over 2.10 because it's the reciprocal, or 0.48. So you're just taking the 1 over to get the reciprocal. In this example, we want to find the F values for a specified area. So for an F curve with a DF of 9, which is the numerator, and 8, which is the denominator, determine the two F values that divide the area under the curve into a middle 0.95 area and two 0.025 areas on the outside. So first, let's find the F value on the right. Because the shaded area on the right is 0.025, the F value on the right is F 0.025 using your DF of 9 and 8, and then F of 0.025, you will get 4.36. That's the number that you're going to get. So that's pretty cut and dry. But now we need to find the F value on the left. And we can use our key fact about the reciprocal value. So the F value is the reciprocal of the F value having area 0.0525 to its right for an F curve with a DF of 8 and 9. So if we go to our table and we find that this latter F value will be equal to 4.10. Then we can take the reciprocal, so 1 over 4.10, and you'll end up with 0.24. And so consequently, for the F curve with the DF of 9 and 8, the two F values that divide the area under the curve into a middle 0.95 area and two of the outside 0.025 areas are 0.24 over here and then 4.36 over here. So what you need to keep in mind is that it is the reciprocal. So we're going to go 9 to 8, and then we're going to go 8 to 9, and then we're going to take 1 over the number to get what we need. So make sure you do some practice on that. Okay, so now we're going to look at hypothesis tests for two population standard deviations, and I have the formula that we'll be using on this page here. F equals, and it will be S1 for the first population squared over S2, which is the second population squared. And we'll go through a step-by-step method. This is the procedure for the two standard deviations F test. So the purpose of this test is to perform a hypothesis test to compare two population standard deviations, so sigma 1 and sigma 2. Our assumptions here are that it's a simple random sample, they're independent samples, and they have normal populations. Our null hypothesis will be that the first standard deviation is equal to the second one, and then we've got two-tailed, left-tailed, and right-tailed options. We'll decide on our significance level of alpha and then compute our test statistic. Now, for this one, we're going to use the critical value approach. And then we'll always use a p-value approach for when we are using technology, or there will be times where I will just give you the p-value and then you can just use it for comparison to make a decision. So just keep in mind that, again, we need this to be a normal population. And if it is not normal, then you have to do a non-parametric procedure because they don't really require normality. Okay, so in this example here, what we're going to be looking at is the Elmendorf tear strength. And this is like vinyl floor coverings. So what we've got here is a table showing brand A and brand B for different floor coverings, and the data is in grams. So at the 5% significance level, do the data provide sufficient evidence to conclude that the population standard deviations of tear strength differ for the two vinyl floor coverings? So the first thing that we're always going to do here, and especially if you're given a data table, is we're going to make sure that the data is normal. And so they've run a QQ plot here, and we can see that it's reasonable to presume that they are normally distributed. So we can go on with our test. So let's determine our null and alternative hypothesis. The null hypothesis, again, no change, no change. The standard deviations of the tear strength are the same. And then for our alternative hypothesis, we're going to do a two-tailed alternative here where the standard deviations of the tear strength are different. We'll decide on our significance level, and it will be performed at the 5% level, or alpha is equal to 0.05. All right, then all you have to do is calculate your standard deviations, and that's where these numbers came from, and square them, and then take them and divide to each other. So you guys really need to stop and make sure that you know how to calculate these standard deviations. And so I'm going to say it again. I've noticed that a lot of you guys are using the wrong formula for the standard deviation in general. So I need you guys to keep in mind that on your formula card, the formula card is always going to show you two different formulas that you can use. It will always have a computational formula, and it will also have a formula for the theory part of it. Now, the theoretical formula, while it will work, you're actually increasing the amount of steps that you're doing, and you're decreasing the precision of it. So you should always be using the formula that is your computational formula. And that is always going to be the second formula on your card. And so you're going to want to cross out any of the other formulas from that. Okay, so make sure that you guys can do this, and then we get our test statistic here of 0.413. Now that we have that, we can make some decisions. Okay, so let's look at our critical value approach for this. So the critical values for the two-tailed test are f, 1 minus alpha divided by 2, and then f is alpha divided by 2. And our df for this is always going to be n1 minus 1, and then n2 minus 1 for this one here. So remember, we had two sets of brand data, brand A and brand B. And so the DF for N for both of them was 10. And so 10 minus 1 is 9. So what you're looking at here is having an alpha of 0.05 and having a DF of 9 and 9. So the critical values are F, 1 minus alpha divided by 2. So that would be 1 minus 0.05 divided by 2 is equal to F, 0.975. And then we'll have F alpha divided by 2. So F 0.05 divided by 2 is equal to F 0.025. From your table, you will look for your F of 0.025 given your DF of 9 and 9, and you'll find it to be 4.03. Sorry. Now, to get the F 0.975, you have to first note that this is the F value having area 0.025 to the left. And so you'll want to apply the reciprocal property of the F curve. And so, of course, that means we're going to do 9 and 9 because luckily that doesn't change. And you'll find the reciprocal and you'll take 1 over, and it will be 4.03 because it is the same. And you'll end up with 0.25. So now we can make a decision. If the value of the test statistic falls within our rejection region, we'll reject our HO. Our value is 0.413. 3. And so it does not fall within the rejection region. It falls in between here. And so we do not reject our null hypothesis. And we can state that at the 5% significance level, the data do not provide sufficient evidence to conclude that the population standard deviations of tear strength differ for the two vinyl floor coverings. And of course, there is a confidence interval procedure, and we call it the two standard deviations F interval procedure. The purpose of this procedure is to find a confidence interval for the ratio of two population standard deviations. Our assumptions are simple random samples, independent samples, and normal populations. And this is the procedure here for our confidence level of 1 minus alpha. We'll use our table to find f, 1 minus alpha divided by 2, and then f alpha divided by 2, with our df of n1 minus 1 and n2 minus 1. The confidence interval then is this formula here. And again, the only thing that's different here is this number that we'll put down here in the denominator. Now, there are some cases when you go to interpret the confidence interval for a ratio of standard deviation 1 to standard deviation 2. So the endpoints of the confidence interval can both be greater than 1. They can both be less than 1. Or one endpoint of the confidence interval can be less than 1 and the other one can be greater than 1. And those are sort of your, interpretations that you can have. We're going to continue using the Elmendorf tear strength example. And so we have the sample data that's on the actual hypothesis test page. So the question here is determine a 95% confidence interval for the ratio of sigma 1 over sigma 2 of the standard deviations of tear strength for brand A and brand B for our vinyl floor coverings. And so we found before in our example that we can reasonably presume that the tear strengths are both normally distributed. We've already covered that. And so we can just apply the procedure to obtain the required confidence interval. So for confidence level of 1 minus alpha, we're going to use our table to find f 1 minus alpha divided by 2, and then f alpha divided by 2 with our df of n1 minus 1 and n2 minus 1. So we want to get a 95% confidence interval, and consequently, alpha here is going to equal 0.05. So we need to find f of 0.975 and f of 0.025 for your df of n1 minus 1 and n2 minus 2, which is equal to 9 and 9. And we did this earlier. We've done that already when we did the actual hypothesis test. And that's really the nice thing about the confidence intervals is you usually have all the information you need to actually run the test. So as you can see down here in step 2, all you really need to do is put in the numbers that you already have. And so that's all down in here. 1 minus the square root of 4.03 multiplied by 128.3 over 199.7. That's your lower end. 2, your 1 over the square root of 0.25 multiplied by 128.3 over 199.7. And what we'll end up with is numbers between 0.32 and 1.28. So you need to stop, pull out your calculator and try this out and make sure that you get 0.32 and 1.28. So how do we interpret? We can be 95% confident that the ratio of the standard deviations of the tear strength for brand A and brand B is somewhere between 0.32 and 1.28, and this is in grams. And so really, if you want to interpret that, it's really saying that it's somewhere between 3.125 times less than and 1.28 times greater than that of brand B. Okay, guys, now you just need to practice. Thanks for watching, and I do apologize for my runny nose.